All right, thanks a lot, Jessica. So I'm Julian Shun. I'm an assistant professor here in CCL. And today I'm going to talk about some recent work that I've been doing on high-performance programming frameworks for static and streaming graph processing. And this is in collaboration with a bunch of people who are listed on this slide here. Okay, so first of all, what is a graph? So a graph is a data structure used to model interactions between certain objects of interest. For example, you can have a social network where the vertices in a graph are the people, and then edges between vertices represent some sort of relationship between the two people. You can also use graphs to model, say, protein networks, where each vertex is a protein, and then there's an edge between two vertices if there's some sort of interaction between the proteins. And there are many interesting questions you might want to ask about your graphs. For example, you might be interested in finding a group of people with similar interests in a social network, or you might be interested in finding a certain substructure in a protein network that has some biological significance. And there are also many other applications of graphs. I'm showing a couple of them here, but there are way more than just these few examples. So graphs are used in connectomics, which is the study of the structure of the brain. So here you have vertices representing neurons, and then there are edges connecting neurons if there's some sort of interaction between them. You can also use graphs to model transportation networks, and you might be interested in finding the shortest path from one location to another location in a transportation network, and that would be solved with a graph algorithm. Graphs are also used in image segmentation in computer vision. They're also used to model the internet, where you have vertices as web pages and then links between vertices corresponding to a hyperlink that exists on one web page and points to another web page. So there are many interesting analytics you might want to run on these graphs. However, graphs today are becoming very large, so they can contain over 100 billion edges. This is the largest publicly available graph. It's called the Common Crawl graph, and it just represents a small fraction of the web pages on the internet. And this graph here has over 128 billion edges, and just storing this graph in memory requires about half of a terabyte. So it's a pretty big graph, and there are even larger graphs out there that are not publicly available. So Google and Yahoo have graphs with several trillions of edges. So if we want to run graph analytics on these very large graphs, we need to come up with high-performance solutions so that we can get our results in a timely fashion. And my work focuses on how to use parallelism to achieve high performance. So we have parallel machines around us everywhere today. For example, your laptop very likely has multiple cores on it. Your phone might even have multiple cores. And you can easily purchase a multi-core machine with tens or hundreds of cores online, or GPU with thousands of cores. You can also rent all of these machines on the cloud at a reasonable cost. So my research focuses on how to use these parallel cores on today's machines to speed up our graph computations. So one aspect of my work focuses on designing parallel graph algorithms and codes to achieve high performance. Unfortunately, parallel algorithms and programs are very hard to write correctly, and furthermore, it's even harder to write them efficiently. And therefore, another aspect of my work focuses on coming up with high-level programming abstractions to make it easier for non-experts in parallel programming to write their own parallel graph algorithms and get high performance without having to deal with all of the low-level details of parallel programming. In today's talk, I'm going to focus on the second of these 2 points here, and I'm happy to talk more about our work on parallel graph algorithms and programs at some other time. So here's an outline of what I'm going to be talking about. I'm going to talk about 2 specific projects. The first is GraphIt, which is a graph domain-specific language that makes it easy for programmers to explore this large graph optimization space so that they can achieve high performance. And in the second part of the talk, I'm going to talk about Aspen, which is a streaming graph processing framework that allows us to do queries on the graph while it's being updated at the same time. And this is pretty useful because many real-world graphs are changing very rapidly. So I'm first going to talk about GraphIt, and I'm going to motivate GraphIt by going over a simple algorithm known as the PageRank algorithm. So this algorithm was initially proposed by Google to rank the relative importance of web pages on the internet. And how this algorithm works is you're first going to initialize some probability mass to all of the vertices in the graph. The probabilities are going to sum to 1, and they also call this the PageRank of each vertex, corresponding to the probability. And then we're going to repeatedly apply this PageRank equation to update the probabilities on all of the vertices. And on every iteration, when we apply this equation, each vertex is going to pass some of its PageRank to its neighbors, and it's also going to receive some PageRank from its incoming neighbors. The amount of PageRank that it gives out is not necessarily equal to the amount of PageRank that it receives. But if you keep running this algorithm, it's going to eventually converge to some probability distribution. And that probability distribution will correspond to the relative rankings of the vertices in your graph. So this is a pretty simple algorithm to write. You can write it in C++ in under 10 lines of code, assuming that you have this graph library that allows you to extract the vertices and edges efficiently. So this is pretty simple code. We have an outer loop where we're going to go for some maximum number of iterations. This can either be some constant or it can depend on some convergence criteria. And then inside every iteration, we're going to go through all of the vertices in the graph. For each vertex, we're going to go through all of its outgoing neighbors, and then we're going to pass some of our PageRank to our neighbor. After that, we're going to go through all of the vertices again, and then compute its new PageRank value based on the PageRanks that it received from its neighbor. So this corresponds to just implementing this equation on this slide. And then finally, we're just going to swap the roles of these two arrays so that we can reuse them for the next iteration. Yes? Yeah, so Google used to use this to rank the search results. I don't know what they use today, but this was originally proposed by Google to rank the importance of web pages. Yeah. Okay. Okay, so this is the C++ code. It works, it compiles, and it runs, but it's not very fast. If you want fast code, this is what the code looks like. So this is the multi-core CPU code for PageRank, which is more than 23 times faster than the code that you saw on the previous slide. And here we're using a parallel machine with 24 cores, but the speed up here isn't just coming from the parallel cores. There are various optimizations that are applied here, including multi-threading, load balancing, and we also have cache and NUMA optimizations to improve the locality of the program so that we can increase the number of cache hits we have, since most of the running time of these graph programs are coming from cache misses. So if we can increase the number of cache hits, then that can improve the overall performance. So ideally, we want the performance of code that looks like this, but we don't want to have to write it ourselves because it's very messy. So it's very hard to write this code correctly, and furthermore, you don't actually know which set of optimizations will give you the best performance. So you have to try different combinations of optimizations, which makes it even harder because every time you change the optimizations, you have to debug your program all over again. And the reason why graph programs are very hard to write today is because there are various optimizations that have been proposed, many optimizations that are designed to give you high performance for graph algorithms. And here I'm listing a subset of the optimizations that have been described in the literature. Each of these optimizations affects the program in certain ways. So it can affect the program's parallelism, locality, work efficiency, and it can even affect more than one of these things. And the way each optimization affects each of these properties of the program will depend on the algorithm. It will depend on the type of graph that you're using, the hardware, and also depends on what other optimizations you're using at the same time. So this is a very hard decision to figure out what the best set of optimizations you should use is. So as I said, the best set of optimizations will depend on the type of graph that you're targeting, whether it's a social network with a power law degree distribution, or whether it's a road network where the degrees are relatively constant, but you have a very large diameter. It also depends on the type of algorithm that you're trying to implement, whether it's a PageRank-like algorithm where you're traversing all of the vertices and edges on every iteration, or if it's more like a breadth-first search where you're only looking at a small part of the graph on every iteration. And finally, it depends on the hardware, whether you're running this on a multi-core CPU machine or a GPU or some other type of accelerator. So we designed GraphIt to make it much easier for programmers to explore this large optimization space so that they can get the best performance for their algorithm, their type of graph, and the hardware that they wish to run their code on. And inside the GraphIt domain-specific language, or DSL, we have an algorithm language as well as an optimization or scheduling language. These are two separate languages. The algorithm language allows the programmer to just specify the logic of the algorithm they're trying to implement. And the code for this algorithm language looks pretty similar to pseudocode you might see in an algorithms textbook. You just have to specify the logic of the algorithm. And then in the optimization language, we're going to specify how we want to optimize particular parts of the algorithm that we wrote. And due to the fact that these are two separate languages, now if you want to optimize your program, you only have to change the code in the scheduling language, and you don't have to modify the logic of your algorithm at all. So the optimization or scheduling representation makes it very easy for programmers to try out different combinations of optimizations just by tweaking some parameters in the scheduling language. And we'll see an example of that shortly. So here's a high-level overview of the components of GraphIt. Yes, there's a question. Yeah, so there's an auto-tuner, which I'll mention briefly. So, question? Yes. Yeah, so we'll actually go, yeah. Oh, yeah. So the question was, how do these two languages relate to each other? I'm actually going to go through an example of this shortly, so hopefully that will answer your question. Okay, so there's an algorithm language in GraphIt, an optimization representation, which includes this scheduling language. There's also an internal representation in the scheduling language that allows the compiler to figure out what sorts of optimizations are legal to apply. And then finally, we have this compiler which will generate efficient low-level code for, currently it's for either multi-core CPUs or for GPUs, but we're also looking into other backends. And then finally, we have an auto-tuner that makes it even easier for a programmer to try to find the best set of optimizations. They can just run this, go take a break, and then come back, and then the auto-tuner will return the best set of optimizations for that particular algorithm, the graph, and the machine that they're running on. So here's a high-level overview of the GraphIt algorithm language. So we have a data structure for representing a subset of vertices in the graph. And then we also have operators for mapping application-specific computations over sets of vertices or over sets of edges associated with a set of vertices. And these two operators here are sufficient to implement a broad class of graph algorithms in our experience. And in the algorithm language, the programmer doesn't have to deal with any low-level implementation details. So they don't have to specify when atomic operations would be required. They don't have to insert code for removing duplicate vertices in a data structure. All of this is taken care of by the compiler. So the compiler, for example, will use dependence analysis to figure out whether there could be multiple threads trying to access the same memory location, and if that's the case, it will automatically insert atomic instructions. So the algorithm language has plenty of opportunities for optimization, as we'll see on the next slide. So here's what the algorithm language code looks like for the PageRank algorithm. So we have this main function down here, and then we're going to loop for some number of iterations, just like we did for the C++ code earlier. Inside each iteration, we're going to call this edges.apply function, which is going to take this update edge function as input. This is an application-specific function, and what this is going to do is it's going to apply this function to all of the edges in the graph. And this is going to pass the PageRank value for each source vertex to one of its neighbors, which is the destination vertex. And then we're going to call vertices.apply, which is going to call this update vertex function, which is going to compute the new PageRank value for each vertex based on the values that it received from its neighbors. Okay, so this is the algorithm specification. There's this label here, S1, which is going to be used by the scheduling language to specify how we're going to optimize this program here. So here we have a scheduling command known as config apply direction, and we're going to refer to this label here, S1, and we're going to specify what direction we want to do this edge apply operator in. And sparse push corresponds to taking all of our vertices and pushing our PageRank values to our neighbors. So it's doing a random write to the PageRank values of our neighbors. And this is the generated code corresponding to this algorithm and scheduling specification. So it's pretty similar to the C++ code we saw earlier. We have a for loop over all of the vertices, and then we have an inner for loop over all of the outgoing neighbors of each vertex. And then we're going to update the new PageRank of our neighbor with our own PageRank normalized by our out degree. You can also add parallelization to this program. So using config apply parallelization and referencing this label here S1, we can specify that we want dynamic vertex parallelism, which means that we're going to parallelize across the source vertices, and we're going to use a dynamic scheduler to do so for load balancing. And here what that does is it's going to turn this for loop into a parallel for loop. So now we're going to parallelize across the different source vertices. And notice here that inside the body we inserted an atomic addition instruction. And this is because now, since we're executing the source vertices in parallel, we could have multiple source vertices trying to update the same neighbor. And in order to guarantee correctness, we need an atomic instruction here. But the programmer didn't have to specify this anywhere. The compiler figured this out and inserted the atomic addition inside the body. Now you can also change the direction that you want to do this edge apply operator in. So now instead of doing a sparse push, we're going to do a dense pull. And what this means is instead of passing our PageRanks to our neighbors, we're going to read the PageRanks from our neighbors and then try to update it on our own PageRank location. So what that corresponds to in the pseudo code, the pseudo-generated code, is we're just going to swap the two loops. So now the outer loop is going over the destination vertices, and then the inner loop is going to loop through the incoming neighbors for each of the destination vertices, and this corresponds to the source vertices. And then now we're going to update the PageRank of ourselves based on the values that we read from our neighbors. And here the compiler got rid of this atomic addition instruction because now you can only have one thread updating any of these locations' new rank of desk because we're just parallelizing over the destination vertices, and then the inner for loop here is a sequential loop. Now you can also apply a cache optimization using this config apply num SSG operator. And what that does is now it's going to generate a whole bunch of subgraphs of our original graph such that the random accesses that each subgraph incur are going to fit in cache. And this is going to significantly improve the locality of our program. And now we're going to loop through each of our subgraphs one at a time, doing the same logic as before, but just restricted to that subgraph. And this guarantees that all of the data that we load in is going to reside in cache as we process this subgraph and before we move to the next subgraph. Okay, so hopefully this answers the question on how the algorithm and scheduling language are related. So we have these labels in the algorithm language which the scheduling language can use to specify how to optimize certain parts of the algorithm. Yeah, you could put an S2 on some other line and then apply some other optimizations, yeah. Okay, so here's the relative performance of these different schedules. So these are all normalized to the performance of the first schedule, which just did a sparse push sequentially. And the experiments here were run on this Twitter graph with 1.5 billion edges on a 24-core machine with 2 sockets. And here the second schedule corresponded to the schedule where we added parallelization across the source vertices. We get a speed up of about 5, which is okay, but we have 24 cores, so it's not actually that good. And the reason why we didn't get that great of a speed up is because there's actually a lot of contention when we're doing this atomic addition to the neighbor locations. There's also load imbalance because the Twitter graph has a parallel degree distribution. However, when we switch to a third schedule, this is the schedule where we're doing a dense pull instead of a sparse push, we're reducing the amount of contention because now there can only be one thread writing to each memory location instead of multiple threads trying to write to the same location. So this improves performance. It's about 12.5 times faster than the original schedule. And then finally, when we add the cache optimization, we get a factor of about 23 over the initial schedule due to improved locality in our program. Yes? How big is the memory of this machine? I think it's about 256 gigabytes. Yeah. So, oh, you mean the DRAM size or the cache size? The DRAM, so this graph fits inside the DRAM, and in the force schedule here, we're trying to optimize it so that the random accesses fit in L3 cache. So this graph doesn't fit in cache, but it does fit in DRAM. Yeah. Okay, so that's a high-level overview of the algorithm and scheduling language. Yes, question?
I guess what I see from the optimization language is that it's very similar to like using a preprocessor or like toggling compiler flags. I'm wondering like what is the benefit that you get for creating like a full-blown like language for this as opposed to having like a configuration file, say.
Yeah, so the question was, what's the benefit of having an entire language here compared to just having a configuration file? So, I mean, a lot of these optimizations we apply here are specific to graph programs. So it's pretty hard to just have a general configuration file to optimize your program because the optimizations here are specific to graphs. And we also need a compiler to make sure that the appropriate instructions are inserted, like when you have multiple threads trying to access the same location. If you just had a configuration file, I mean, the compiler can't really figure that out, a general purpose compiler. So that's why we needed a specific compiler for our graph optimizations to make sure that everything that we applied was legal to the graph program.
So I guess what I'm hearing is that the important bit about the optimization language is the compiler itself.
Yeah, yes. Yeah. So most of the work is done in the compiler. It will interpret all of the commands that you gave it in the algorithm and scheduling specification, and then do code transformations to make sure that all of the optimizations get applied and all of the appropriate synchronization and deduplication logic gets inserted in the right places. Yeah. Okay. So in the previous example, I was just tweaking the parameters in the scheduling language by hand, but you can actually use the auto-tuner, which will automatically find the best set of optimizations. And in fact, using the auto-tuner, we were able to find some sets of optimizations that are even better than the ones that we found by hand initially. So here are some performance results comparing GraphIt's performance to state-of-the-art graph processing frameworks for CPUs. And here the numbers correspond to the slowdowns relative to the fastest implementation for that particular algorithm and data set. So the data sets are on the y-axis, the algorithms are on the x-axis. So the data sets are all social networks except for this RD graph, which is a road network, high diameter road network. And then we have PageRank, breadth first search, connected components, and single source shortest paths. We also have other algorithms not shown on this slide here. So we see that GraphIt usually achieves the best performance. It has a value of 1. And the reason why it's able to get such good performance over these existing frameworks is because it's able to explore orders of magnitude more schedules than these existing frameworks. So the existing frameworks only have a couple optimizations for certain types of graphs, so they do well in certain settings, but then they do poorly in other settings. So they don't achieve performance, high performance consistently. And these numbers, I should mention, are kind of out of date. So we've actually improved the GraphIt compiler recently so that we're actually almost matching these other frameworks for the ones that are not one here. Yes?
I guess, like, why are the competing state-of-the-art solutions not able to explore as many possible optimizations?
Okay, so the question was, why are these existing frameworks not able to explore the different sets of optimizations? So each of these frameworks are actually proposing their own set of optimizations. So I mean, if they wanted to, they could actually implement these other optimizations into their language as well. One difference between GraphIt and these other languages or these other frameworks is that GraphIt has a compiler, whereas these other frameworks here, they're libraries, so they're written in C++. So if you want to apply these optimizations inside these frameworks, some of them would be pretty complicated to implement. It would be pretty tedious for the programmer to have to do all of these code transformations. For example, we're able to apply these global optimizations such as data structure transformation, where you change from a struct of arrays to an array of structs. But this requires modifying the code in many different locations, and this is pretty tedious to do in one of these libraries here. Yes?
What is the LJ data set? Why does
So the LJ dataset is a live journal. It's a pretty small graph. I mean, currently, actually, GraphIt matches the performance of Ligra. There is some optimization that we didn't do earlier with regards to memory allocation for this small graph. It actually matches it now, yeah. Okay, so I talked about the original GraphIt system just now. Recently, we've extended GraphIt to support what's called ordered graph algorithms. So the original GraphIt was designed for unordered algorithms where the vertices don't have any priorities on them. So on every iteration, it doesn't matter what order we process the vertices, and the answer is still going to be correct at the end. But it turns out that for certain graph problems, there are these ordered parallel graph algorithms where we're actually maintaining priorities on these vertices dynamically. And these ordered graph algorithms can achieve better work efficiency and, as a result, better performance in practice. So I'm not going to go into too much detail about these specific algorithms, but I just want to say that we've recently extended the algorithm and scheduling language in GraphIt so that we can support these ordered graph algorithms. So we needed to add this priority queue data structure to the algorithm language and then optimizations on this priority queue data structure to the scheduling language. And we've compared to state-of-the-art graph processing frameworks for ordered graph algorithms, and we found that we're able to achieve the best performance in almost all of the cases here. So it's up to 2 times faster than Galois, and then 17 times faster than Julian. And then more recently, we've been designing this GraphIR. It's an intermediate representation inside the compiler, which captures many of the optimizations that you would want to apply to a program, but this GraphIR is hardware independent, so it doesn't depend on any specific platform that you're running on. And this makes it much easier to extend the GraphIt compiler to support other backends, because now you don't have to re-implement the entire compiler yourself. You just have to provide implementations for specific instructions in the GraphIR. So right now, we've developed 2 backends for GraphIt, a CPU backend and a GPU backend using this GraphIR, and they share a lot of common infrastructure. So this makes it easy for someone who has their own domain-specific accelerator to extend GraphIt to support graph algorithms on their architecture. Okay, so that was the GraphIt DSL. Next, I'm going to talk about Aspen, which is a streaming graph processing framework that we've developed that allows us to run queries on the graph while it's being updated at the same time. So many real-world graphs are changing rapidly in real time, and we want to be able to run algorithms on the graph even though it's changing. So in the streaming graph processing model, we have a stream of updates coming in, and we also have a stream of queries, and each of these queries are asking some question about the graph. For example, whether one vertex is reachable from another vertex, whether the graph is connected, what the clustering coefficient of a specific vertex is, and so on. And the goal of a streaming graph processing framework is to be able to support both updates and queries at the same time while guaranteeing serializability. And what this means is that the answers you get from the queries should be consistent with some sequential ordering of the updates in the queries. And the reason why we want this is that it makes the answers much easier to reason about, and it prevents us from finding certain structures in the graph that never actually existed, but were due to artifacts of running the updates and queries concurrently. And secondly, we also want to be able to achieve low latency and high throughput for both the updates and the queries. So existing work falls into 2 broad categories for streaming graph processing. There are single version systems as well as multi-version systems. So single version systems, as the name implies, maintains a single version of the graph, and this single version is the latest copy of the graph. So it doesn't store any historical data, it only stores the most recent version of the graph. One thing about single version systems is that you need to separate the graph queries from the updates in order to achieve serializability, because if you only have one version of the graph and it's being modified, then the algorithm that you're running on the graph might produce some weird results if the graph is changing underneath. The other type of system is multi-version systems. And for multi-version systems, they support multiple graph snapshots. And these snapshots are immutable, so they're not changing, and this allows us to run queries on the latest snapshot without worrying about the graph changing while the algorithm is running, because the new updates will get buffered and included in the next snapshot. However, in existing work, the snapshots they use are not space efficient. They basically just copy the entire graph, so the space needed is linear in the size of the whole graph. It's very expensive to create, so they can't create these snapshots too often. And this leads to high latency for the updates, because it's going to take a long time from when an update happens to when it actually gets reflected in the latest snapshot. And for the single version systems, we also get high latency because the queries have to wait for the updates and vice versa, so we get high latency for one of the two types of operations, or even both if we keep switching the type of operations we're doing. So in our work, we followed the multi-version system approach, and we developed Aspen, which uses much lighter weight snapshots than existing work. And these lightweight snapshots are very quick to create. They only take logarithmic space and time. And this allows us to basically create a snapshot for every graph update operation. And this allows us to achieve low latency for queries and updates that are running concurrently. The main idea behind Aspen is to represent the graph using what's called a purely functional tree. These are also known as persistent trees in the literature. And purely functional trees, one property is that they can be updated efficiently in logarithmic time and space while retaining an old version of the tree. So you can actually keep around previous states of the tree. And Aspen uses a tree of trees to represent the graph. So we're going to have a purely functional tree over the vertex identifiers, and then for each vertex, we're going to store a purely functional tree on its outgoing edges. And now when we want to apply an update to the graph, what we do is we're going to look at the path in which the update is going to affect in our tree. So let's say this is the edge tree for some vertex v, and we want to insert the neighbor 12 to v's edge list. So what we're going to do is we're going to check what the path is where 12 would actually traverse if we wanted to insert it into this tree here. It's going to start at 8. It's going to go down to 11, and eventually it's going to be a right child of 11 because we want to preserve this binary search tree property so that we can efficiently find neighbors in this tree. And what a purely functional tree does is it's going to copy this path from the root down to the leaf where we did the insertion. And this path here is going to store pointers to subtrees in our old version of the tree because these subtrees didn't actually get modified. But the nodes on the path here did get modified, so we copy this path here. And the one property of this tree is that the height is logarithmic, so that means it only takes logarithmic time and space to create these snapshots for every update. And with these lightweight snapshots, we can now do queries concurrently with updates to the graph. So in Aspen, we have a pointer to the root corresponding to the latest version of our graph. And each node also has this reference count, which stores the number of pointers that are pointing to it at any given point in time. So the most recent version of our graph has a reference count of 1, the root corresponding to that. Now when a query comes in, we're going to grab the latest version. We're going to grab a pointer to the root corresponding to the latest version and increment the reference counter to 2. Now, when this algorithm here is running, someone else could come in and modify the graph. And then what we're going to do is we're going to copy the path in the tree that got modified. We're going to swing this latest version pointer to point to the root of the new tree now. We're going to decrement the reference counter on the old tree and increment the reference counter on the new tree. And notice here that this path that we copied has pointers into subtrees of the old tree because those parts of the tree didn't change. And then now if another query comes in, it can actually access a different version of the graph. And now it's going to bump up the reference count to 2. And notice here that these two queryers are looking at different versions of the graph. And these versions are not going to change once the query starts, which allows us to achieve serializability. And then once this query is done, it's going to release the pointer to this root, which decrements the reference count to 0. And once the reference count of a node becomes 0, we're going to garbage collect it so that we don't keep around old data. And in this case, we're going to garbage collect this root here. And after we delete that root, it's going to cause some of these other nodes to have a reference count of 0, and then we delete those recursively. But we're not going to delete these nodes here, which still have a pointer pointing to it from the path that we copied. Okay, so using these purely functional trees, we can easily support concurrent queries and updates, but there are some disadvantages of representing graphs using trees. First is poor cache usage. So we're going to have to store one tree node for every vertex and every edge in our graph, and when we traverse this tree, every time we go down one level, it's going to cause a cache miss because these nodes are going to be stored in random locations in memory, and when we chase this pointer, that's likely going to cause a cache miss. It's also space inefficient to represent graphs using trees because we have to store these tree pointers for every node in our tree, and this takes a lot of space. And we also have to store metadata on the tree nodes, such as this reference count that I talked about. And we also lose the ability to perform integer compression, which is a common compression technique used to reduce the size of static graphs. And the compression techniques require the edge list to be stored contiguously in memory, but with the tree representation, they are not stored contiguously in memory. So to store this large common crawl graph, which I mentioned at the beginning of the talk, it requires close to 7 terabytes of memory. So this is for the symmetrized version of the common crawl graph, which has 225 billion edges. So this is quite a bit of memory, and it can be prohibitive for most people to run this code if they need 7 terabytes of memory to do so. In contrast, the state-of-the-art compressed graph representation for static graph processing takes only about 350 gigabytes to represent the same graph. So there's about a 19.6x overhead using the tree of trees representation. So our next goal is to try to reduce this space overhead, and we do so by using this data structure, which we call a C-tree. So it's a compressed version of the purely functional tree data structure. The C-tree has a chunking parameter, b, and it also has a hash function h, which is used to make random decisions in the tree construction. And what we're going to do is we're going to select the elements in our tree as heads with probability 1 over b using our hash function h. So if this was our original tree, then we selected 3 of these nodes as heads, so the ones colored in gold here. And then in the C-tree, we're just going to build a tree on these head nodes. For all of the non-head nodes, we're going to attach them to the closest tree node that has a value smaller than it. So for example, here, nodes 28 through 40 get attached to the tree node 27 because it's the closest tree node that has a value smaller than it. There are some values here that are not attached to any tree nodes because there were no tree nodes selected that had a value smaller than them. And we're just going to store these in what we call the prefix of the C-tree. So the C-tree contains a prefix as well as a tree on these head nodes. And inside each of these nodes, we have a contiguous array of these integers here. And because we now have these contiguous arrays of values, we can easily apply integer compression. So we can store the differences between consecutive IDs here instead of using the full representation to store those integers. And then we can use variable length encoding to reduce the number of bits we need. We're also reducing space because now we only have to store these pointers and the reference counts for many fewer nodes, only for the head nodes. We don't have to store it for all of the nodes. So we also show how to support parallel bulk insertions and deletions on the C-tree in pretty much the same bounds as in standard parallel binary trees. I'm not going to talk about the algorithmic details here, but there's a paper on this if you're interested in reading more. So with this C-tree representation, we're able to bring the space down to about 700 gigabytes. So it's now 9 times better than our original representation, and the overhead over the static graph representation is just a factor of 2, which we think is a pretty reasonable trade-off to make to be able to support queries and updates concurrently. So the API for Aspen is an extension of the Ligra programming API. So this was work that I developed in the past. But Ligra is designed for static graph processing, so we introduced some new primitives for allowing the graphs to be updated. So we now have this acquire operation where a thread can acquire the latest snapshot of the graph, and a release operation where a thread can release the snapshot that it acquired. And then we also have operations for doing bulk insertions and deletions of vertices and edges in the graph. Aspen supports what's known as single writer multi-reader concurrency, which means there can only be a single task that's updating the graph, although there could be multiple tasks that are reading the graph. But that single task that's updating the graph can be a parallel task, so you could have multiple threads in that single writer task. But the reason why we need single writer multi-reader concurrency has to do with serializability issues. Okay, so we ran a bunch of experiments evaluating the performance of Aspen. I'm just going to show you 2 experiments here. So for the first experiment, we measured the latency of running queries in isolation without any updates changing the graph. And then we also ran an experiment where we had queries concurrently with an updating thread that's modifying the graph. So we ran this experiment on a 72-core machine with 2-way hyperthreading. So there's one hyperthread updating the graph while the remaining hyperthreads are just running queries. For this example, it's running parallel breadth first searches. This is for the concurrent setting, and then in the setting where we don't have any updates, then we just have all of the hyperthreads running the parallel breadth first searches. And here I'm showing the latency of these 2 scenarios. So the scenario where we don't have any updates is in gold, and the ones where we have one updating thread is in red here. And the overhead of having a thread updating the graph is less than 3%. So this is a pretty small overhead, and part of the overhead is due to the fact that we just have one fewer thread doing the queries. We also ran this experiment where we had more threads doing the updates and fewer threads doing the queries, and the latency was basically just proportional to the number of threads that were doing queries. So this shows that the fact that we're updating the graph at the same time doesn't really affect the performance of any queries that are executing. Yeah, so this is a stream of individual updates, but you could also apply batch updates. If you had multiple threads in your updating, in your writer task, they can actually be batch updates.
In the database area, usually one assumes that only 3 to 10% of the operations are reads.
Yeah. So here, most of the operations are reads. So we have 143 hyperthreads doing the queries, and then only one thread doing the writes. Yeah. So the other experiment that I'm going to show you is the throughput of doing batch updates in Aspen versus Stinger, which is a state-of-the-art graph streaming framework. Stinger is a single version system, so it only maintains the latest version of the graph, but it's shown to have superior batch update performance compared to other frameworks. And here, we're varying the batch size and showing the throughput in log-log scale, and we can see that Aspen's throughput is much better than Stinger's, 1 to 2 orders of magnitude faster depending on the batch size. And this is due to the fact that the C-tree data structure just supports updates much more efficiently than Stinger's data structure. Okay, so that was the Aspen framework. If you're interested in learning more about either of these 2 projects, here are links that you can visit. At each of these links, there's source code that you can download and run on your own machine. There's also documentation on how to use the API if you want to write your own graph programs in either of these programming frameworks. So I'm happy to take any more questions now.
So I see in the beginning of the second part, it mentions the update for the edges, but does it support update of the vertices?
Yeah, we can support vertex updates as well. Maybe it wasn't shown on my slide, but yeah, you can do vertex updates. Since we have a purely functional tree for the vertex IDs as well, so you just need to copy the path in the vertex tree if you want to add a new vertex or delete some vertex.
You mentioned something related word is the Stinger. So is there any open source frameworks that supports a streaming graph already?
Sorry, could you repeat the last part of the question?
You mentioned another related word is Stinger
Yes.
library. So is there any open source framework that can support streaming graph?
So Stinger is an open source framework. So it supports streaming graph processing. As I mentioned, it's a single version system, so it only keeps around the latest version of the graph. In contrast, Aspen keeps track of like multiple versions of the graph. Yeah, and there, like on one of the earlier slides, I've listed a couple other systems. So all of these other ones are open source as well. So let me go back to this slide. Yeah, so here are some of the other ones that are open source, and they support graph streaming.
Okay, thank you.
Yeah.
So for the GraphIt example you gave us, you had the option to kind of control how much data was being fit into the cache.
Yeah.
Is that something that auto-tuner system you explained actually tunes? Because I would imagine for different hardware, right, if you've got different size of cache, you're going to want to change the size of those subgraphs.
Right. So the auto tuner is run on a specific machine, so it's going to tune the scheduling language for that particular machine. So it will fit it in the cache for that machine. If you use another machine, you're going to have to rerun the auto tuner.
So could you just explain what that last parameter then was? I thought it was the size of the subgraph, but what, it was like 10
Let's go
or
back to
something.
this.
Yeah. This one here, yeah. What's the 10?
Oh,
represent?
the 10 here is the number of subgraphs that we want to create. So that's going to depend on the cache size. We want to make sure that each subgraph fits into cache.
Okay.
Yeah. So we have documentation on the website. There aren't actually that many functions to use, and then each function has maybe like 2 or 3 parameters. So yeah, you just have to read the documentation, and if you don't want to do that, you can run the auto tuner, and it will automatically figure it out for you. You can go take a coffee break and come back and see the results.
Thank you all for joining, and thank you so much for
Yeah, thanks, Jessica.